Goedemorgen, bonjour, good morning. It's my great pleasure to be in the city of my birth and where I lived the first 25 years of my life before heading to the United States for my studies. But today I want to share with you that we are living in a super special moment. It's one of those moments that we are at the beginning of an exponential curve, an exponential growth in artificial intelligence technologies, and I will tell you why and what the impact of that will be to the world. We all live in a linear time. In fact, all of us think very linear ways when it comes to space and time. And if you're in exponential, it's like constantly accelerating in a car. When you drive at constant speed, it's comfortable, no matter really how high the speed is. But when you're constantly accelerating, it's actually often a scary time, but also a time of great opportunity. The first such exponential curves was for computing. In the 70s, on a centimeter square computer chip were about 1,000 transistors. Today, 10 billion transistors or switches are on a computer chip. And as a result, of course, we have supercomputers, we have mobile devices that are extremely capable. And as you will see, as a result of that, everything around us will become intelligent in the future. And this was called Moore's Law. The number of transistors doubled about every 18 months. Then there is a second law called Metcalfe's law. In fact, Bob Metcalfe was a colleague of mine. In fact, I arrived after he left Park, but while he worked there, he invented the Ethernet and came up with Metcalfe's law, which says that the value of a network is proportional to the square of the number of users on the network. So the more users or devices are connected to the network, the more value it creates. And of course, this has led to a huge explosion of data, images, videos, other information, as well as to many of the most valuable companies that exist today. And then today, similar, a couple decades later, we are at with this explosion of data, together with the powerful compute power, has now enabled artificial intelligence to become a reality. So we're at the beginning, and I would really stress only the very beginning of this exponential curve of AI, and in fact, it's about artificial intelligence accelerating new knowledge creation in a very, very fast way, and progress is really being made in a super fast way, and I'll share some of that with you today. So from an AI point of view, we recently exited the phase that is called narrow AI, deep narrow AI. It is AI we all experience in our lives. It is when Facebook recognizes your face or who you are, or it is a kind of AI that's used in virtual agents that you can chat with and that can answer all your questions about a very, very specific product. And its initial value creations, enterprises are starting to embed it within their work processes. All the way on the right is what is called general AI. And that is, we predict more, after 2050, but it is a very wide range if you speak to experts of when that become a reality. That is when a system really knows and can create new knowledge and can do what humans can do today. And then in the middle, today, we're in this phase of broad AI, which is really going to be very disruptive and very pervasive across all industries. Let me give you some examples. So in the narrow AI, it's all about huge volumes of data. This face recognition has been trained on billions of images. It is a single task, a single domain, and the system can have superhuman accuracy and also at super speed. For example, in healthcare, detecting skin cancer leveraging deep neural networks, which really became very powerful around 2012 when that became, at least for image categorization, the preferred way of doing AI. So for skin cancer, it's super good. However, with these deep neural nets, they can't explain what they do. And that's where we get into the second phase now, which is broad AI. In order for it to be much more useful by physicians, by cities, by banks, in agriculture, etc., often you work with small data. A hospital might have a small number of patients, or me as a human, I have even less data about my personal health. So you need to be able to train these artificial intelligence models with way smaller data, and that is a key research that is being done both at IBM as well as across in institutions across the world. It's also multimodal. Not only is it being able to read an X-ray image, for example, it's also being able to read patient records, it's being able to hear, it's being able to get input from multiple sources and make meaning and sense out of it. And it has to be explainable. I mean, a system has to be able to tell you why does it think you have skin cancer, or why can you not get a loan. It can't just say, okay, the computer told me so. So explainability is a key area of research today. And as I mentioned, general AI, it's still farther out. It is that kind of AI that people often are scared about, and universities and others are working on it, but it's more broad autonomy, and again, it's multiple decades from now. So another thing that is really happening now, thanks to the computer power being able to be embedded all around us, and being really tiny and low cost, is that AI is moving to the edge. Today, most systems are both trained, so the learning happens in the cloud, and also the inferencing. Once the model knows and has been trained on something, the inferencing happens in the cloud. In the future, that will move to the edge for many reasons. Not only it reduces, of course, the power consumption, the bandwidth required, and also the privacy. For example, today my Fitbit does, everything goes to the cloud, it gets analyzed, it comes back. All of this should and can be done at the edge. And only exception only should it go to the cloud and then trigger some action, whether it's from a physician or from family members or somewhere else in the back-end processes of an enterprise. And here you see some examples that where a lot of intelligence is being embedded, obviously in autonomous cars that need to make very quick decisions locally within an intersection, for example, or medical devices or drones. And recently, just a few weeks ago, IBM Research announced the world's smallest chip. It's smaller than a millimeter by a millimeter. It contains all of the processing power, memory, input-output for readability, etc. It's about the size of a grain of salt. And these kind of devices can really ultimately be embedded everywhere to make everything around us smart and know what we need and what we want, and really have personalized many services and experiences, again, whether it's in your home, at your work, in your car, in the hospital, etc. So a couple examples I'm going to give. One is healthcare, one is the environment. Within healthcare will truly be transformed by all these technologies coming together. We are really becoming data, and our doctors are becoming software. In fact, today, the IBM Watson healthcare business, we view it as augmenting physicians to do a better job, to really be able to understand what is the latest, how to diagnose earlier, and then what are all the treatments that are available, including those that are still in medical trials, reading the hundreds of thousands of publications that are happening a year or every couple of years, and making sure that all this knowledge is captured and at the fingertips of a physician. But as you can see, a lot of data is available or will become available about individuals, about each and all of us. A couple examples that I want to give here is one project that we did recently was working with Pfizer on the trials for a new drug for Parkinson's disease. Patients with Parkinson's disease, how they behave and how they feel depend heavily on whether the medicine is working or not. So on our campus, in one of our 21 locations around the globe, in Yorktown Heights, we have a home that's also on the campus, and we installed it to make it truly a smart home. So there are sensors everywhere. And so so here is a picture of the home. And so the reason the value here is that in an unobtrusive way, the sensors can look at humans that come and live in the home for a few days, for example, patients with Parkinson's disease, and can really understand how they move. They can observe, for example, with visual sensors, how a patient moves around, what the patient is doing, and depending on that, we can then know, the algorithms will understand whether the medicine is working well or not. And again, many companies are interested in being able to do this kind of tests instead of having the patient go to the doctor's office once a week, once a month, which is basically very random sampling of data points. So here we can say the house can see. Another very valuable thing that artificial intelligence will be able to do is help individuals with mental issues. For example, today in the US alone, there are 63 million psychiatric interviews or therapy sessions done on a yearly basis. It's very expensive, time-consuming. So how can artificial intelligence really help understand and early on diagnose if some of our friends and colleagues or family members have a mental issue? And so what we have done, again, in the same house, there are microphones, and you come in and you can talk about your family, or you can talk for a few minutes, and the system will, of course, translate from voice into natural language, and then depending on how your dialogue is structured, the system will be able to assess what kind of, if there are any mental issues. It can also assess if you had a little bit too much to drink, or if somebody was abusing drugs. And so we have done this with about 100 patients, where we actually knew the patients had been diagnosed. So initially you train the model on data that you know that what category the patient fit in. And so these models now, we're moving to test them out with more patients and really understand. And so again, this will really help in a non-obtrusive, very low-cost way, being able to assess the challenges. And in fact, there is a website here. You can go to the IBM Research website and talk for a few minutes in the computer, and it'll give you some answers that you might either want to know or not want to know. But so this is really powerful. This is how AI will be able to help people in the future. So that was my healthcare example. Let me quickly switch to the environment and indeed creating more livable cities. Our research lab in China has been working with the government, initially the city in Beijing, to understand how to lower the pollution level, and especially the pollution of small particles, 2.5 micron particles and below, because that's very bad for your health. And so over the last 3 years, working with the government, we have been able to help them lower the pollution level significantly. In fact, I was there, and they showed me like a big command center, big terminals, showing the actual real-time pollution level in the city at any given point in time. And so we're also moving to water and soil pollution. But let me tell you what's the technology is embedded behind it. So what we have done, and the city of Beijing has done, is install air quality sensors every square kilometer in the city, so very, very hyper-localized, together with satellite data and a lot of other data, including the weather company data. IBM acquired the weather company maybe 2 years ago. And so within the weather, in some places in the world, I know in Belgium it's often less accurate, the predictions, but in many places the prediction is very accurate, 10, 14 days out. So if you can know the real pollution, predict what the weather will do in the next 10, 14 days, you can actually predict pollution levels in the future. And when you can predict, you can take action and prevent the pollution to naturally become as high as it would be if you don't intervene. And so in Beijing, they then take localized, very localized action on shutting down or minimizing pollution so it doesn't get to the peak levels that would have been achieved without this AI embedded at the edge. And now that's rolled out to more than 300 cities in China and already pilots in multiple other countries around the globe. So I talked about AI being embedded everywhere. I'm going to touch on two other topics. The next topic is trusted ecosystems, right? With the internet, the digitization of information took off. I would say our point of view is that blockchain, which is the underlying technology of Bitcoin, for example, the underlying blockchain platform, will do for trusted transactions what the internet did for information. Meaning, if you want to transact in physical goods, for example, or in very valuable things like whether it's stocks or other land ownership, you can capture this in a ledger instead of each of the parties having an individual ledger where everything is recorded. You can have a shared ledger that's very transparent, meaning if 5 companies or 50 companies work together, when I make a change in the ledger, it has to be approved and it will be seen by everybody. Then it will be encrypted and a new block in the blockchain will be created that cannot be changed. So you can always go back and know exactly what happened to a particular good. And so the first project, this was on by our lab in Kenya, working with the European lab, and now it's a joint venture, an actual business, was working on logistics, on shipping of goods from one country to another country. In a typical shipment, there might be, for example, if you move fruit from Mombasa to Amsterdam was the actual example with it, there were like 30 entities involved. At customs, a lot of paperwork, and one lost document can mean that your container is stuck in a port for more than a month. So in fact, the paperwork associated with shipping goods around the globe was super, super expensive. And so with the blockchain, you can have all these entities, let's say these 30 entities, all have visibility, transparency in what's happening. It's all digitized. Everything is really clear. All the transactions are clear. And it significantly reduces the cost of shipping goods, and the trust is significantly increased. One of the, of course, and then if you put artificial intelligence on top of the blockchain, for example, we did a project with diamonds which have to be ethically mined. There is something called the Kimberley Regulations. It's a 25-page document. So you can, as you track the diamonds from the mine to the finger or wherever they end up, you can actually make sure in an automated way that all these requirements for ethical mining and the distribution of these diamonds are satisfied in like 2 minutes. I mean, this is super fast, which these are things which are normally very hard to track. Another example is a project we did with Walmart, and again, it's now a big network. Walmart and their suppliers are all part of it. It is, again, being able to track food. The first project was also done in the lab in China, tracking pork from the farm to the table. But now we're looking at, for example, tracking organic food to make sure that it's truly organic as it goes through the value chain. Another key reason that the companies really like it is if there is an outbreak, like an E. coli outbreak today, and in fact there was just one a couple of weeks ago in the United States, there was E. coli on lettuce, but nobody knew where lettuce came from. Which farm does it come from? Suddenly no consumer buys lettuce anymore. It's taken off the shelf. I mean, the whole market, I mean, everybody suffers. And so with the blockchain and with what we call a crypto anchor, either a smart chip embedded in the boxes or labels on the actual goods, You can, again, super fast, in a couple minutes, track down, okay, this lettuce is contaminated, and by the way, it's only this farm. So very valuable. And then with that, an additional level of really very interesting and powerful research that is happening is not only track the goods, but do the DNA sequencing of all the microorganisms in the food itself as it travels along the value chain. So we have created a huge database in the lab in California of the biome of the bacteria that live in actual food. And this is valuable, again, going through all of these different locations to actually measure it in case there is an outbreak of E. coli, for example, to come back to that example, you can quickly track down at which moment in this whole value chain did it actually happen. Because it might not have happened in the farm, it might have happened in the processing house, for example. So collecting this whole, we call it metagenomics database, is also going to lead to multiple additional insights in the future. So finally, I want to touch on accelerating the knowledge creation, new knowledge creation itself. So at this moment, I was mostly talking on quickly categorizing and understanding whether it's diseases or, again, environmental situation or the food, what's happening to it. This is now about new knowledge creation. And a specific example is materials discovery. There are about, if you're looking at a new molecule, for example, for a new pharmaceutical drug, or for a new coating or material you want to use in one of your processes, it is a very manual process. There's also a huge amount of information available. About 100,000 papers a year are published. That number to me seems super high, but that's what I was told exists, or the knowledge base continues to increase. No individual scientist obviously can stay up to date with all of these huge amounts of information. There are many known materials, but there are way more materials that we don't even know about today. And every one single material that's selected takes hundreds of hours to really get it to a state where you can decide, okay, we're going to proceed forward and make a new drug out of it, or okay, it's a failed experiment and we learn from it. So with artificial intelligence, you can actually, that's the bottom arrow there, you can actually, with natural language processing, you can create what's called a knowledge graph about particular materials by quickly, automatically reading all that information, understanding what's in graphs, what's in images, and put it in your knowledge base, whether it's patents and papers. And then you can, of course, leveraging supercomputers, you can start to do simulations and modeling. And these two things together will create new knowledge graphs that scientists can then use to query, to come up with properties and define more rapidly the right molecules and materials to go look at and explore, and so much faster get to the right answer. And one area where we have also applied this is working with actually several companies, and again, this is IBM Research working with several companies. It's to create novel, like to be creative and come up with novel perfumes or novel spices, flavors. And so today, again, that's a very manual process. There are thousands of ingredients you can use for a perfume, for example. There are hundreds of thousands of formulas today. It's actually very complicated and a big data problem. And there are really trillions of possibilities. And also a perfumer or a flavorist, somebody who tastes or smells and can really create these new flavors or perfumes. It's a very highly expert, deep expert, and it requires a decade of training or more to be super good. The same for wines or being in the beer city for beer. When you create novel flavors, it's very difficult. So one of the things we have done is we have trained an artificial intelligence model, put all the formulas in, trained it on understanding how these ingredients come together to create certain flavors or certain aromas. And based on that, you can do many, many things, right? The first things you can do is tell companies or the existing formulas, are you using this super expensive ingredient? But by the way, if you substitute it for this much lower cost ingredient, the aroma will be the same and the end product will be lower cost. So that's a fairly easy thing to implement. More difficult is to create new flavors and new tastes, right? As flavors and new aromas. But that's exactly what the system is starting to do. It's starting to suggest, okay, how about this? This could actually be fairly good. So we're experimenting with that, and really, this is now about creativity, creating new items. In fact, we also did a project with food, with all kind of rice dishes. We trained the whole system on rice, creating different creative rice dishes. We call it Watson Chef. And the AI system came up with a dish where there was mostly salt with a little bit of fries on top of it. And so anyway, these systems are not foolproof yet, but it's the beginning of really having artificial intelligence that can truly be creative. So in addition, right now, when the neural nets are trained, they come up with a new flavor or a new taste. It is still a human that actually smells or tastes it and will say yes or no, this is good or not good. Some of the additional sensors, right? Before you heard me talk about seeing and hearing and reading, we are developing sensors based on microelectronics that will be a digital nose or digital taste. So it's a set, an array of sensors on the left that is to detect different gases or aromas of about, I think this example is 30 different sensors that are then connected to a neural net to be able to categorize a whole set of different aromas or different tastes. On the right is the project researchers are doing with wine in our Zurich lab, to be able to categorize wine and actually by tasting it. Again, sensors that sense liquids. And here it's applied to food. You can also see how that could be applied to healthcare if you use these sensors to really, for example, put in your toilet and you can read the components of many different fluids of humans. So digital nose and digital taste, research have been working on it for a while. But again, I think now is the moment that many of this will become a reality. So one other quick topic is quantum computing. Because quantum computing will truly accelerate discovery even more, especially materials discovery. So in a regular digital computer, the unit is a transistor which is either on or off, a 0 or a 1. In a quantum computing equivalent is what's called a qubit. And a qubit, instead of being on and off, it's like can be in a three-dimensional set of states, a huge number of different states at the same time. And so they can interact with each other, just like atoms and electrons interact with each other. And in that way, these computers will be able to simulate, for example, molecules in a way that traditional computers today, even the supercomputers, just cannot do. Especially more complex molecules like caffeine in your coffee. These are the kind of molecules that traditional computers can no longer simulate in an accurate way. Today, the quantum computer is about 50 qubits. It's been increasing from 5 qubits last year to 50 this year. This technology has been in the labs for 25 years or more. My first job after my PhD was at IBM Research, and then I went to Xerox for 25 years, and now I'm back. And even 25, 30 years ago, they were already working on quantum computing. So it's a super difficult to make system. It operates at almost 0 Kelvin because you need to have these particles in a very, very stable state to interact with each other. But again, we're at the verge of this exponential curve of this technology becoming a reality. In Nature magazine recently published IBM research results of modeling simple molecules. These you can still model on a traditional computer, but as the more and more qubits will become available, this system will quickly overtake what traditional computer can do. And in fact, some of the things this system will be able to do is decrypt all the encryption that exists today that encrypts a lot of the confidential information, financial information, the internet. And so there is a lot of research happening in creating new encryption methodologies that will be secure for quantum computers. But again, there is a website, you can go there. You can actually do experiments on a quantum computer. 75,000 users from all continents have done about 4 million experiments. This is open source, it's free. You can get there and experiment with it. And in fact, you can also take a course, right? Quantum computer is actually super complicated. And so we have worked with MIT, and MIT EDX now has a course that you can take to really be trained in quantum computing. There's 5 levels. This is basically part 1. So with that, let me end with the kind of principles that are super important in this era of artificial intelligence. Number 1, the creators and the users of AI have to have the purpose in mind. At IBM, we strongly believe and know that the purpose is to augment humans in doing a better job, augment the physician, augment the scientist, augment financial services companies to be able, and decision makers, to be able to make better decisions and provide better personalized care. Number 2, it's super important that the system is transparent, that it explains why a certain answer was achieved, that it doesn't use your data to train models for other companies or other users. So that's what we call also ethical AI, that the models are unbiased or less biased than even humans are today. And number 3, it's super important that all of us, especially enterprise and universities, train individuals, both new students as well as all of us that have been in the industry for a long time, in acquiring the new skills of this era, whether it's around AI, blockchain, quantum. It's important that all of us, or the individuals, know what they need in order to transform their own jobs and their companies. Okay, oh, great, sorry. Thank you, excellent.